Okay.
We're good, yep.
We're good? Okay. We'll see about that. All right. So today is just kind of an anomaly. It's going to just kind of be a work day. But there's some things that I want to go over that you understand with this lab when you start to answer those questions, because you guys are kind of in the heart and soul of that now. Because y'all pretty much get done with your trials? Okay. So here's the key assumption that we're making initially, is that whatever the weight is that's hanging down is what's creating that centrifugal force. So when you get to the last question on that lab, and it's got like the rubber stopper, and it asks you to draw all the forces acting on it, okay? You know, have that visual. It's like, okay, what's that going to look like? So when that rubber stopper is going around, what things could possibly be acting on that stopper? Now, here's one thing that I will flip out if you draw, okay? So as this thing's going around like this, right? Okay? Is there any force, think this through, as this thing's going around, are there any forces acting from the inside pushing it out against the string? Absolutely, categorically, no. Okay? What is creating the tension in the string? What'd you say?
Centrifugal force.
Yes, because here's the deal. What's happening is this. Your rubber stopper wants to travel in a straight line. Okay? Now, to demonstrate that, so let's kind of go to the, take up the camera. We're gonna just kind of go toward the back right here. Okay?
Uh-oh. Uh-oh.
Hi, cousin. Oh, I thought you were gone. I didn't see you come in. Who's this?
I think it's for Zach and Aiden, probably.
Okay. So here's what we're going to do. So the battery gets curved right here. So I'm going to take this hovercraft and I'm going to put it in this book, and I'm going to swing it around like this on the floor. And then I'm going to stop it, and then we want to try and see what the path of this thing is going to be. So I'm going to have it here. I'm going to swing it around like this, and I'm going to stop it about right here. So there's 4 options that can happen to that rubber stopper when I stop it. Option number 1 is actually going to curl out this way. So I'm going to be coming around like this, and it's going to slightly take a curvature out like this. Option B is just going to go in a straight line like this. Option C, it's going to continue to curve, but not as much, okay? And it'll end up over here. Option D, it'll continue that same radius that it was on and end up and probably hit about Colby's foot, okay? So it can curve out, go straight, it can continue to maintain a slight curve, or it'll maintain like that same curve that it was on and hit Colby's foot. So, how many vote it's going to curve a little bit out? Okay? B is going to go straight. C is going to take a little bit of a curve. Okay? How about it's going to maintain the exact same curve? Okay, so most voted B, a few voted C. So, let's see what happens. Oh, it's hard on an old man. Okay. What did it do?
Straight line.
Went exactly on a straight line, right? Now, because look at Newton's
Sorry, camera.
first law. It's like such a weak hovercraft with the battery in charge. So, what's Newton's first law of motion?
Object in motion stays in motion.
And that, now, technically, more importantly, an object with a certain velocity will maintain that velocity, right? but there's two parts to a velocity vector, all right? There's the magnitude and there is the
Direction.
direction. So when that thing left that meter stick, was there any forces acting on it to cause a change in that direction?
No.
No, so what did it do?
It's
Just
straight.
went in a straight line, okay? So when that thing came around and I stopped it, as soon as it left, it wants to maintain that constant velocity, meaning it wants to go in a straight line, and what's the only reason it slowed down?
Friction.
Yeah, there was a little bit of friction because the battery hadn't charged, so it wasn't a full hovercraft, okay? Got that? All right, so, back we go.
I'm sorry. Sorry. Put my button up there. Not the worst.
But again, here's the difference. If you're Polly the Penguin driving your car and you take a hard right-hand turn, Polly the Penguin's going to think, wow, I was pushed up against the side of the car, okay? When you make that hard right-hand turn. But again, here's what you have to understand. There's nothing inside forcing him against the car door. He just wants to go in a straight line, and you feel that action-reaction against the car door. But there's nothing pushing him out. He just wants to move in a straight line. So it's like he's running into the door, okay? So with that string, when you go around, there's nothing pushing the rubber stopper out. The rubber stopper just wants to continuously move in a straight line. Okay, so when you get to the question where you have to calculate the experimental error, you're going to use mv squared over r for trial number 4. So, Kelsey, so on your trial number 4, let's kind of see what you would end up with. What was the mass of your stopper on trial number 4?
0.0294.
0.0294 kilograms. What was your velocity on trial number 4?
I got 33.3, but I don't know if I did it right.
That seems a bit
which
fast,
one?
but
For number 4,
how'd you get your velocity?
I took my circumference times pi divided by period. I got 10.6.
You mean your radius times 2 pi? Because your circumference is 2 pi r, right?
Wait, I think you just do meters over second. Okay, I did 2 pi r divided by period,
Yeah.
and I got 33.3.
Okay.
I got 11.
Yeah. 33.3.
I know, that's huge, but
Okay, but let's just say that's what you
Really
got.
big.
Let's just say with it. For the sake of argument, let's say what you got. Okay? And then we're going to square that. And then you're going to divide by a radius of 0.008 meters. So, based upon this, she's going to calculate this. So, do this. Go, you're crunching the numbers. Do that. Take 33.3, square that, times that mass of the stopper, divided by 0.8.
is that 2.4?
Yeah, 0.0294.
Yeah, I think you're right.
33.8.
33.8
I know what I did.
newtons. Okay, here's the deal. On trial number 4, the weight of that hanging mass was 3.92 newtons. Okay, so that's why I'm thinking something has gone wrong here, do it.
I got it.
What did you do wrong?
Well, I multiplied the 2 pi r times pi again.
Oh,
The
okay.
answer.
That would explain it.
So it's just the, yeah, I got it.
Okay.
Sorry.
Okay. But anyway, so that's going to be your process. Okay, so on trials 4, 8, and 12, you're going to calculate centripetal force using mv squared over r. Then, it's like, I picked one. So, and then you're going to compare that to 3.92 newtons. So that's going to be the same for everybody because everybody had a 0.4 kilogram mass on trial 4. So you're going to take 3.92 newtons minus what you get from mv squared over r divided by 3.92 times 100. Okay? There you go. So the next question, you want to calculate the centripetal acceleration. So basically, that centripetal acceleration, just use v squared over r, okay? Just make it simple. You already have the velocity calculated for trial 4. Square root of that, divide that by 0.8. And then once you get that centripetal acceleration, once you get that number, divide that by 9.8 meters per second squared to get your g's, okay? Got that. You're going to calculate the centripetal force needed to keep the Earth in orbit around the sun. That if you do that one right, what's that number? Is that number 15? Mm-hmm. So that number 15 should get you an answer with an exponent of 10 to the 22nd. Okay, it's a pretty big number, but we're on a big rock, so it's going to take a lot of force to keep us in orbit around our star. And then on number 16, you're going to calculate the centripetal force needed to keep this person on the Earth as the Earth spins. Okay, and that answer on number 16, I'll give you 2 hints. It's a 2 for Wednesday. Your answer should be less than the weight of the person. Okay, so if you take 70 kilograms times 9.8, it's going to be a pretty big number. Okay, it's about 700 newtons. The centripetal force needed to keep this person is much less than that, and that's a good thing. Because if the centripetal force needed to keep us on this spinning rock was more than what gravity could provide, we wouldn't be here having this discussion because we would go flying off. Kind of like water on a spinning tire. Okay, that water goes flying off because it's going so fast that it can't stay on there. So the same thing's going to happen if the Earth. So if your answer in terms of the centripetal force needed to keep that 70 kilogram person on the Earth was bigger than the gravitational pull, the person would go flying off. It would be like me taking this thin string and trying to swing Hank the bowling ball on from the end of it. It's not going to happen. Okay? So, as a matter of fact, your answer to number 16 should make a not so good GPA. Okay, so when you get done with number 16, it should make a not so good GPA. Not completely horrible, but just not so good. Okay? All right. Now, let's talk about a couple of problems on this blue sheet. Okay? So let's talk about that. Huh?
It's stuck.
Okay. So, I want to talk about question number 3 at the top. And we've done it with problems like this, but I want to make sure everybody's cool with this. So, you've got this airplane, okay, horribly drawn airplane, but you get the point. It's a glider. And you're going around on the end of a string, and you're going to go faster, and both the speed and the radius of the circle are constant at double the original values. You don't know what's going to happen to the centripetal acceleration. Okay. So, there's 2 ways that you can work this problem. One is you just make up numbers, okay? Literally, that's the easiest thing to do, you make up numbers. So what's the easiest velocity that you could pick? 1, okay? I want to let the plane be moving at 1 meter per second. What's the easiest radius to pick? 1 meter, okay? So if this plane is moving at 1 meter per second with a radius of 1 meter, that's going to have a centripetal acceleration of 1 meter per second squared. Okay, kind of cool. Now, look at what's going to happen. Then, we're going to go faster as more wires played out until both the speed and the radius are double their original values. Okay? So my new centripetal acceleration, I'm going to call that AC prime, because this is the new situation, right? So instead of 1 meter per second, what am I going to do?
2.
I'm going to put 2 meters per second. But what's going to happen? It's going to get squared. And instead of dividing by 1 meter, I'm going to divide by 2 meters. So when I do this, I get 2 squared, otherwise known as 4 divided by 2 gets me
2.
So what's going to happen to my centripetal acceleration? It's going to double. Okay? Now, that's if you like numbers. Okay? And that's a very valid approach that you can take with this. Now, The more mathematical one is you go, oh, okay, centripetal acceleration is just v squared over r. Okay, cool. Now, my new situation, what am I going to do to that velocity? Double it. So that's going to be 2v squared, right? What's going to happen to my radius? It's going to double. So that's going to become 2r. So 2v squared, Lexi, is what? 4v squared divided by 2r. So I get 2v squared over r. So that's the other way that you realize that it's going to double. So I don't care which approach that you take. Put in numbers, whatever, okay? Or you can go with the more pure mathematical approach and work with variables, okay? It doesn't make me any difference. It makes me no difference. Now, let me give you some hints. When you get to like question number 3, or problem number 3 down below. So here's this tire, right? It's got like knobby tires. And there's a pebble that's stuck in there, right? So something's got to hold that pebble in. I want to say, oh, it's a certain amount of friction. So you got 20 grams. What are you going to have to do with the 20 grams?
Turn it into kilograms.
Change that into kilograms, right? Now, here's what you have to pay attention to. Notice that I've given you a diameter of 0.712. Okay? You have a diameter of 0.712. What do you have to have for the equations? Radius. But realistically, this is why you typically measure diameters, because it's easier to measure the diameter than it is to try and guess where the center is and then measure the radius. So that's why a lot of times in these type of problems, you're given the diameter because that's physically easier to measure. And then you just take your diameter and divide it by 2. So then you have a radial frictional force, 20 newtons. So that's the frictional force that's acting to hold that tire on there. So it's like me taking the green spinny thing and putting that on there. Oh, okay, hey, there's enough frictional force to hold it on there. But if I go fast enough, it's going to go flying off. So there's a limit to what that frictional force can do. So basically, what I would recommend on number 3 is that you start with this idea. Centripetal force equals mv squared over r. Get in the habit of solving these equations first, because it's so much easier to solve with variables than it is with numbers, okay? Especially once we get into the planetary motion stuff, and you're going to be dealing with like the mass of the Earth and diameter of the Earth, these really, really big numbers. The sooner you embrace this idea of solving the equation first, the better off you're going to be. Now, when you get to number 7, okay, there's 2 ways you can work number 7. One option is that you go velocity equals 2 pi r over t. This is an option, okay? So you're talking about the Earth as it goes around the sun, right? So I've given you the radius, okay? 1.50 times 10 to the 8th kilometers. And I've given you the period of 365 days. So one option is you calculate the velocity, and then you take that velocity and you put that into v squared over r. That's an option. It's not a good option because it's a god-awful amount of work. Because you have to calculate the velocity, and then you have to square that velocity, and then divide back by the radius. It's much simpler if you just go straight into 4 pi squared r over t squared. That saves you that step of finding the velocity separately and then putting it back into v squared over r. If you just go straight into 4 pi squared r over t squared, there you go. Now, on number 7, why could you not calculate the force needed to keep the Earth in orbit around the sun? Yeah, you don't have the mass. You couldn't do that if you tried. So the only thing we can calculate is the centripetal acceleration, and that should be a pretty small number, okay? Your answer to number 7 should be a pretty small number, like very much less than 1. Now, when you get to number 8, okay, and here's what you have to understand on number 8. So, the hammer thrower track and field rolls around at a rate of 2 revolutions per second. So here's this hammer throw. So imagine this is like the hammer, and you're spinning it around. And when they do this, they actually, it's pretty cool. They actually like go around like this, right? So they're spinning at 2 revolutions per second. So here's what you need to decide. It's 2 revolutions per second. Is that frequency or is that period? It's frequency because it's an event per unit of time. Now, there's 2 ways that you can work this problem. I don't care what you do, okay? Because at the end of the day, you want to calculate the inward force that must be exerted on the ball. So one option is that you realize that, well, centripetal force is mass 4 pi squared r over t squared. But here's the problem. That's the frequency. But how can you take frequency and change that into period? Yeah, they're inverses of each other, okay? So on your equation sheet, on kind of this side over here, you've got right here where it says general information, you have t equals 1 over frequency. The whole key to this is that you realize what I've given you is the frequency, not the period. Because if it was period, it would say, oh, the time for 1 revolution is 0.2 seconds or whatever that is, okay? That's the difference. So, so to get period, you can take 1 over the frequency, okay? And you're going to get a number, and then you can slam that in there. That's an option, okay? That's option number 1. If you like that option, go with it. It's cool, right? Now, the other option is a little bit fancier, okay? It's actually simpler, but it's a little bit, but you have to see a little bit. So if I came in here and put 1 over frequency squared, because 1 over frequency is equivalent to period, right? Okay, same thing. So then that becomes mass times 4 pi squared r 1 over frequency squared, right? So frequency squared is in the denominator, so what's going to happen to it? It's going to flip up. So you can also write this as mass 4 pi squared r frequency squared. And again, you end up with the same units because that's in kilograms, that's in meters, frequency is 1 over seconds, but that gets squared. So you still get kilograms, meters per second squared. So you can either find period separately and put it in here, or you can just keep frequency and put it there like that, okay? I don't care, it's up to you, it doesn't make me any difference. So, when you get to number 9 is a similar type thing, okay? You have a centrifuge that's spinning at 5,000 revolutions per minute. That 5,000 revolutions, is that frequency or is that period?
Frequency.
That's frequency. So, you want to calculate the centripetal acceleration. So again, on your centripetal acceleration, you can go 4 pi squared r over t squared, or you can go 4 pi squared r times frequency squared. Okay? I don't care which one you do. It doesn't make me any difference. It's a personal preference for you. But here's what's important. No matter what, you have revolutions per minute. What do you need to change that into? Instead of minutes, you need it in terms of seconds. Okay, so keep that in mind. When you get to number 10, here's the setup on question number 10. Okay, Mustang, 0 to 26.8, 5.6 seconds on a straight run. Okay, and that's pretty fast. So then you got a Mini Cooper, okay, a Mini Cooper, right, which in no way is a speed car, but it's a cute little car. But let's say you go, oh, I want to experience, here's the setup thing. Oh, I want to have the same acceleration as if I'm driving a Mustang, right? But the Mini Cooper is going to undergo centripetal acceleration. The Mustang is going to undergo linear acceleration, okay? So visualize this. You want to figure out what you have to do with that Mini Cooper, okay, to travel it around, just hit myself in the head, as that thing goes around in a circle without hitting something like your head. So as that thing goes around in a circle, what conditions do you need to have that centripetal acceleration equal to the linear acceleration of the Mustang? Okay, so I kind of take you through that step by step and saying, okay, hey, you know, you're going from 0 to 26.8 in 5 seconds, calculate your linear acceleration, and then set that equal to your centripetal acceleration, where you have v squared over r. Okay, so that's the thought process on that. Okay, I am done. You have the rest of the time to work on these things. So